Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week, and I've entitled this Weird Stuff About the Sun, the Earth, and Our Atmosphere. A lot of this we've talked about before, but maybe not quite to the degree of detail that I'm going to talk about it today. And as I was preparing this, my mind started going in different directions, so if this seems a little scatterbrained, that's the reason why you would perceive it to be that way. So let's go on ahead and get started here. We're going to start off with our little Earth, okay, our little planet, and we're going to talk about the fact that on January 4th of 2025, about a month ago, we were at our closest point to the sun, 91,403,000 miles, 403,954 miles from the Earth. Now, coming up on July 5th of 2025, we will be at our farthest point from the sun, 94,508,040 miles from the Earth, okay? Let me get out of the way so you can see that. And that is a difference of 3,104,086 miles. So you might be thinking to yourself, okay, so why is it cold in the wintertime if we're 3 million miles closer to the sun than we are during the summer? Well, that's like saying, yeah, if I put my hand closer and closer to a hot stove, it's going to feel cooler. No, it doesn't work that way. Don't do that, okay? But the other things that come into play that actually determine that we're cold in the winter and hot in the summer, that's what we're going to talk about now. So let's say we're looking at the Earth from the side, and the equator is right in the middle there, and it's surrounded by the atmosphere. And we've got a couple of human beings, one at the equator and one at a more northern latitude, let's say Caribou, Maine, or someplace like that. So at the equator, let's say it's the first day of spring and the sun is directly overhead at the equator. So the sun's rays are coming in basically like shining a flashlight directly in somebody's face, okay? If you shine it at an angle to somebody, the light is going to be spread out over a greater distance and the light intensity is going to not be what it is if you were to shine it directly in their face. So think of this poor person here as getting a flashlight right in their face, and as a result, it is very, very hot, irregardless of how far away they are from the sun. Now, if it was a 40 million mile difference, then yeah, you'd have to take that into account. But 3 million compared to 91 and 94 really isn't all that big of a difference. Now, let's consider that person at a more northerly latitude, and can you see how the path length there? This is a short path length through the atmosphere, but because this is coming in at an angle, then this path length is actually considerably longer. So a good bit of that solar radiation is scattered out, it becomes more diffuse, and it's spread out over a larger area. So as a result, it's not nearly as warm at those northern latitudes as it is farther south, where the sun only has to go through a shorter distance of the atmosphere, and also the light rays are much, much more direct, okay? So in summary, the sun's rays travel through a greater distance of the atmosphere the farther north you go, and thus more scattering occurs, and also it's less direct sunlight, okay? It's spread out over a larger area. Okay, so then I started thinking, let's get down to the local scale here. Instead of taking a look at the whole Earth, let's take a look at this guy sitting right here on the Earth with the atmosphere enveloping him on all sides, okay? Now, let's say that this person is at 23.5 degrees north on the first day of summer, okay? So the sun is directly overhead in the middle of the day. It's solar noon. So those sun's rays are coming straight down, and again, it's direct, it's right in your face, and it's going to warm up significantly because of that. But at sunrise and sunset, okay, and this applies anywhere, okay? It doesn't have to be at the equator or Caribou or whatever. It's just the principle of the fact that when the sun's higher in the sky, the rays have to travel through less of the atmosphere. But at sunrise and sunset, they have to travel through a much greater distance of the atmosphere, and so that's why it is cooler at sunrise and sunset as opposed to the more direct rays that have to travel through a shorter distance of the atmosphere in the middle of the day. Now, there is something called Rayleigh scattering, okay? And there are all sorts of different sized particles in the atmosphere that scatter light, okay? So the particles like atoms and molecules that are really, really teeny, that is described as Rayleigh scattering, and that's defined as when the particles are much, 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 much smaller than the wavelength of the light rays. So obviously atoms and molecules are going to fall into that category. So there is an equation. This is the only equation I'm going to show you here, okay? But the scattering is proportional to 1 divided by the wavelength of whatever the light rays are to the 4th power. So remember, like 10 to the 4th power is 10 times 10 times 10 times 10, okay? So whatever the wavelength is, you're going to take it times itself 4 times, okay? Now, red, the color red, has a longer wavelength than blue, which has a shorter wavelength, okay? So if red is a bigger number and you're taking it times itself 4 times, that's going to make the denominator in this fraction very, very big, and 1 over that is going to be very, very small. So red light is not going to get scattered all that terribly much. Blue light has a shorter wavelength, and so when you take that times itself 4 times, the denominator will not be as big, and so there will be more scattering, and this is the reason the sky is blue, is that blue light is scattered more than the longer wavelengths like the yellows and the oranges and the reds. However, at sunrise and sunset, since the sun's rays have to travel through a greater distance of the atmosphere to get to you, as a result, there is so much scattering that is going on that all the blue light is gone, okay? And the only thing left are the longer wavelengths. And so this is why at sunrise and sunset, you get an orange to a red color to the sky, whereas during the middle of the day, the whole thing is blue. So again, the distance that the light rays have to travel through the atmosphere is critical in terms of not only how warm and cold it gets, but also what the sky looks like at those various times of the day. All right, I hope that made a little bit of sense. That is bonus weather video number 2 for this week. Number 3 will be coming up on Friday, and the next daily update, of course, coming up tomorrow. So you all take care. Have a wonderful, a few minutes left of your Wednesday evening, if you're even still up. And if you're not and watch this tomorrow, I hope you're having a great Thursday, and we'll talk to you later today. All right, take care, everybody. See ya.